Alkenes. Molecular formula and degree of unsaturation. The general molecular formula for an alkane is CnH2n plus 2. In the case of alkene, since it has got a double bond, there is going to be 2 hydrogens less, and therefore the general formula is going to be CnH2n. In the case of cyclic alkane, since it has got a ring structure, one ring structure, it is going to have 2 hydrogens less from the original alkane, and therefore it is going to be CnH2n. And similarly, in the case of cyclic alkene, it has got one ring structure and also one pi bond. So together, there is 2 degrees of unsaturation, and therefore there should be 4 hydrogens less from the original alkene or 2 hydrogens less from the general alkene. Okay, so it's going to be CnH2n minus 2. So the general formula for a saturated hydrocarbon is CnH2n plus 2, and you have to subtract 2 hydrogens for every pi bond and every ring. So basically, the degree of unsaturation is the total number of pi bonds and the rings that is present in the compound. And we can calculate the degrees of unsaturation using this formula, where you're going to multiply the number of carbons by 2, and you're going to add the number 2, and you're going to calculate the number of nitrogens that are present in the molecule, minus the number of hydrogens, minus X, which is basically the number of halogens present in the compound, and the whole thing should be divided by 2. Now let's do an example for calculating the degree of unsaturation. Find the degree of unsaturation of a compound which has the molecular formula C7H6O2. So again, what we are going to do is we are going to plug in the numbers for carbon, hydrogen, and oxygen in this formula. So how many carbons do we have? There are totally 7 carbons, so it's going to be equivalent to 2 times of 7 and plus the number 2, and there are no nitrogens, and therefore it is going to be 0. And the number of hydrogens is 6, and there are no halogens, so again it's going to be 0. And the whole thing should be divided by 2. So it is going to be 14 plus 2 minus 6 divided by 2, and that's going to be equivalent to 10 divided by 2, or it's going to be equivalent to 5. So for this molecular formula, the compound is going to have total of 5 degrees of unsaturation. It could be a mixture of double bonds, triple bonds, or it could be even rings. Compounds with molecular formula C8H14. This compound has got only carbons and hydrogens, and therefore it would be much easier for us to determine the degree of unsaturation. All we are going to do here is we are going to find the general formula for the saturated hydrocarbon, which is CnH2n plus 2. And from here, we are going to find out the total number of carbons and total number of hydrogens this molecule is going to have. So since we have total of 8 carbons here, we are going to put the value for n equals 8, and then we are going to also calculate the total number of hydrogens that this compound would have if it's going to be saturated. So that is going to be C8H18. So from here we are going to subtract the total number of hydrogens that is missing in this compound. So when we subtract it, then it's going to be 4 hydrogens, right? So if it's going to have 4 hydrogens, then the number of degrees of unsaturation for this molecule is going to be 2, right? And this 2 degrees of unsaturation could be either 2 double bonds, or it could be 1 double bond and a ring structure, or it could be 2 rings, or it could be a triple bond. Okay, when you say a triple bond is going to have 2 pi bonds, right? And therefore, there is going to be a total of 4 hydrogens. Saturated and unsaturated hydrocarbons. What is the difference between saturated and unsaturated hydrocarbons? Saturated hydrocarbons do have only single bonds. Alkane is an example for saturated hydrocarbons. And unsaturated hydrocarbons, they can have double or triple bonds. Alkenes have double bonds and alkynes have triple bonds. And both fall under the category of unsaturated hydrocarbons. This is alkyne. This is an example for alkyne, and to be more specific, this is acetylene or ethyne. Nomenclature of alkenes. For finding the name of alkanes, we are going to pretty much follow all the rules that we have covered in alkanes, but we are going to replace the ane in alkane, ane in the parent chain, with ene. So the alkenes are going to end with ene. Let's do some simple examples. First, let's go on to this compound right here. This compound has got a double bond and there are 2 carbons in here. Therefore, this is going to be ethene. And this one has got a total of 3 carbons and therefore this is going to be propene. This has got a ring structure and the double bond is present within the ring structure and the number of carbons in the ring structure is 5. Therefore, the name of this molecule is going to be cyclopentene. And similarly, for this one, it is going to be cyclohexene since you have got a total of 6 carbons. For alkenes which are greater than 3 carbons, then we have to give the numbering for those molecules because when you say butene, a butene could represent 1 butene and also 2 butene, right? Because of the position of the double bonds. 1 butene is something which is going to have the double bond between the first and the second carbon, whereas 2 butene is going to have the double bond between the second and the third carbon, right? So after the 3 carbons, you're going to make sure that you give the numbering for the alkenes. And similarly, 2-hexene is going to specify only one compound, whereas hexene is going to represent different compounds. You can have 1-hexene, you can have 2-hexenes, and you can also have 3-hexene. All these are going to be constitutional isomers. Here, the double bond is going to be treated as a functional group, which means it is going to get the lowest possible number. So in other words, your parent hydrocarbon chain should have the double bond in it with the lowest possible number. So we cannot choose this one to be our hydrocarbon chain or the parent chain because it doesn't include the double bond. We have to consider this double bond within the longest carbon-carbon chain. So having that as the longest carbon-carbon chain, we are going to make sure that the double bond gets the lowest possible number. So which means we are going to number in this direction. So on the second carbon, we do have a propyl ring, the propyl group. Okay, so and the total number of carbons here in this longest chain is 6 and therefore it is going to be hexene. And where is the double bond present? The double bond is actually starting on carbon 1. So therefore this is going to be 2-propyl 1-hexene. Alkenes can exist as cis and trans isomers. For compounds, for alkenes that exist as stereoisomers, you have to put the cis or the trans in front of the molecule. For example, this is 2-pentene and this is also 2-pentene. But how are we going to differentiate these 2 compounds? One is a cis isomer where the 2 bulky groups are on exactly the same side of the molecule on the top portion, whereas this one right here is a trans alkene where the 2 bulky groups are on opposite side along this plane. Okay, so we have to denote the stereoisomers with the cis and the trans in front of the name of the molecule. Nomenclature of dienes. When you have 2 double bonds in a hydrocarbon, then it's going to be called as diene. The parent name is going to be diene. Let's do some simple examples here. Let's take a look into the first compound. So on this first compound, there is only one chain, right? So we need to go either from left to right or from right to left. Which direction are we going to choose? Remember, the double bond is going to be treated as a functional group, which means it needs to get the lowest possible number. So from which direction can we get the lowest possible number for the double bond? If we go from here, then that puts the double bond in the 3rd position. But if we go from left to right, that puts the double bond in the 2nd position. So we have to definitely go from left to right. So here is the numbering for the chain. And since there are 7 carbons, it's going to be called as heptadiene since there are 2 double bonds present in it. Now, heptadiene could mean like several things, right? Because the position of the double bond has not been specified here. We have to make sure that the position of the double bond is specified in our name, right? Only then it would be an appropriate name. Now, where is the first double bond present? It is starting at the 2nd carbon. And where is the second double bond starting? It's starting at the 4th carbon, right? So therefore, this is going to be 2,4 heptadiene. Let's go on to the next one. There is only one chain, so we don't have to be worried about trying to find the longest chain. Okay, and for this molecule, we have to go from right to left because that puts the double bond in the 1st position. If we go in the other direction, that puts the double bond in the second position, so we definitely don't want to do that, right? Since it has got 5 carbons, it's going to be called as pentadiene. And let's also position the double bonds. It's actually at position one double bond is at position 1 and the other double bond is at position 3. So therefore this is going to be 1,3 pentadiene. Next example, for this molecule we can go from this direction or we can also go from this direction because there is some sort of symmetry in this molecule, right? The parent name for this molecule is going to be pentadiene, and on pentadiene is present 2 double bonds, one at position 1 and the other one at position 4 diene. Okay, these two compounds where the double bonds, where there is alternate double and single bonds, is called as conjugated dienes. So dienes can be classified under 2 different heads. One is conjugated diene and the other one is isolated diene. Conjugated dienes is going to have alternate double and single bonds, whereas isolated dienes, they are not going to have alternate double and single bonds. There is not any connection between the 2 double bonds. Okay, so these two are examples for conjugated dienes. And this one is an example for isolated diene.